So in section 1.6, we're going to talk about inverse functions. We'll find inverse functions informally and verify that the two functions are inverses of each other. We'll use graphs to decide whether functions have inverses, determine whether functions are one-to-one, and then find inverse functions algebraically. So the first thing we're going to get into is how do you verify that two functions are inverses? So what you're going to use is composition. And you're going to do f of g of x, and if that simplifies to x, and then g of f of x, and if that simplifies to x, then what you can conclude is that f and g are inverse functions. So what that means is if you did the composite of f with its inverse, you'll always get x, or the composite of the inverse with f, you'll also always get x. The other thing that's interesting is, remember, when we find inverse functions, we switch x's and y's. So what happens is that the domain of the original function is the range of the inverse, and the range of the original function switches to the domain of the inverse. So if you know the domain and the range of the original function, then you just switch those, and those become the domain and the range of your inverse function. So for this example, we're going to find the inverse and then go through that verification to show that they are actually inverse functions. So first, if our function is x minus 6, then we would replace the f of x with a y. Oops, that was supposed to be a 6. And then to find the inverse, we switch x and y and then solve for y. So y equals x plus 6. And then go back to the original name. So the function was f of x. So we would say the inverse of f is x plus 6. And then if we want to verify, so if we do f of f inverse of x, that means that we're plugging the inverse into the x coordinate in the original function. So we would have x plus 6, which is what we're plugging in here, and then minus 6. So you would get x. And then if you go the inverse of f of x, or the inverse of f of x, we do that same thing, but this time we're plugging the x minus 6, the f function, into the x of the inverse. So we would have x minus 6 plus 6, which simplifies to be x. So because both of those composites simplified to be x, we can say that the functions are inverses of each other. So here, verify the inverse functions algebraically, show that the functions are inverses of each other. So when you're asked to do that, you have to show that f of g of x will simplify down to x. And then when you do the composite of g of f of x, that also simplifies to be x. So if we first start with f of g of x, so we're plugging g into the x coordinate. So we'll have 2 times the cube root of x plus 1 over 2, and then we'll cube it from that cubed right there, and then minus 1. So when we start to simplify that, the cube root and the cube simplify, and you have 2 times x plus 1 over 2 minus 1. So in the simplifying, remember this 2 out front is really like a 2 over 1, so you wouldn't distribute the 2 to the numerator and the denominator. When you have a 2 in the numerator and a 2 in the denominator, those will simplify. And so then you're left with x plus 1 minus 1, which just gives you x. So you have the first half, and then we have to do the same thing again, but for g of f of x. So this time we're plugging our f of x function into our x variable. So we have the cube root of 2x cubed minus 1. So that's what we substituted in right there. So then plus 1 over 2. And then we have to work to simplify. So this minus 1 plus 1 is 0, so you have 2x cubed over 2. The 2 simplify, so you have the cube root of x cubed, which just simplifies to be x. So then the next thing is the graph of an inverse. And remember, if you have the graph of a function and you have a graph of the inverse, then they should be reflections over the line y equals x. So if you have a point A, B on the function, so whatever the x coordinate is and the y coordinate is, they'll switch, and on the inverse you would have the point BA. So if you have to graph an inverse, sometimes the easiest way to graph an inverse is to look at the coordinates of the function and then just switch those x and y coordinates. So to have an inverse function, a function must be one-to-one, which means that no two elements of the domain, so no two x values, correspond to the same element of the range. So what that means is graphically, one-to-one, like if we looked at this graph right here, this would be one-to-one, because a one-to-one function passes the vertical line test and the horizontal line test. So what that means is if it passes the vertical line test, then you have a function. If it passes the horizontal line test, so if you were to draw a horizontal line, really blue is not the best color there. So if you were to draw horizontal lines, those will only pass through once, which means that the inverse then is also a function. So remember that the vertical line test tells you if f of x is a function. And the horizontal line test, if a graph passes the horizontal line test, then it tells you that the inverse is a function. And so if they pass both, then you have a one-to-one function. So if you look at this graph right here, and we wanted to decide if this was a one-to-one function, if we were to draw a horizontal line through right here, we would see that it passes through the graph twice. So it does not pass the horizontal line test, which would mean that f of x squared, f of x equals x squared, is not one-to-one, right? Which is what it says right here in really small letters. Okay. It's still a function. F of x equals x squared is a function because it passes the vertical line test. It's just not a one-to-one function, which means then that the inverse is not a function. All right, and so we did this a little bit already, but finding an inverse algebraically, you will switch your x and y, and then we'll solve the y for y. And then remember, you need to go back and replace, instead of saying y equals, you need to go back to whatever the function's name was and use the inverse of that function kind of as that final part of your answer. So if we need to find the inverse of this function algebraically, first we'll start by saying y equals 5 minus 3x over 2. We can switch the x and y. So 5 minus 3y over 2. And so now you use algebra to solve for y. So you could multiply both sides by 2. Subtract 5. So 2x minus 5 equals negative 3y. And then when you divide by negative 3, that's your inverse. But remember, we're not leaving it as a y since it was named f of x to start. So our final answer would look like the inverse of the function is 2x minus 5 over negative 3. And then this last example is a little bit trickier because we have a square root. So the first thing that I would think about here is what the domain. So the domain for this, if we were to solve, is going to be reals greater than or equal to 3/2. And your range would be reals greater than or equal to 0. So now if we go through and find the inverse, so if we say x equals the square root of 2y minus 3, so we would have to square both sides. equals 2y minus 3. And then when we solve, we get x squared plus 3 equals 2y, or y equals x squared plus 3 over 2. So we would say our inverse is x squared plus 3 over 2. But because this was restricted up here, our inverse is also going to be restricted. So we have to give the domain for this. So remember that the domain for your inverse is whatever the range of the original function is. So this is true for reals greater than or equal to 0.